if you want to look it over, we can do it next time too.
I'd like to see 1 and 2, but if you can't do all of that today, that's
Okay.
perfectly fine.
We have, yes, I can totally do that. Okay, so okay, so number 1. So we have saturated liquid water in a piston cylinder. We're given a starting volume and a starting pressure, and then the pressure is held constant. Okay, so first we want to calculate the quality. And we can calculate the quality using any property. We know that the volume that we start with is 0.10. And it's, okay, so let me write it out like, excuse me, state 1 and state 2. And it's a saturated liquid here. And we're given that as a saturated liquid, our specific volume is 0.001. And then at state 2, it's we just know that the true volume is 10. This is cubic meters. Okay, so from state 1, we can say...
State 1 is also volume of 0.1.
That's right, that's right. And so from this, we can say that 0.1 is equal to 0.001 times the mass. And so the mass is 100. And so from that, then we can say that the specific volume at state 2 is 10 divided by 100. So that's 0.10. And now we can calculate the quality because we know that 0.10 is equal to 1.694x plus 1 minus x times 0.001. So let's see. This is 0.099 is equal to 1.693x. And so x is equal to 0.058.
So 5.8% liquid?
Yeah, that's right. No, that's wrong. 5.8% vapor.
Got it.
Yep. And then now we want to calculate the work of expansion. That is the integral from the starting extensive volume, which is 0.1, to the finishing volume, which is 10. And the pressure is 1 times 10 to the 5. And so this is 9.9 times 1 times 10 to the 5, or so that is 990,000 joules.
Thank you.
And then 2. So we have this tank. And water is flowing into it at a rate of 40 kilograms per second. And water is coming out of it at a speed of, I'm going to just calculate that number. So 4 times square root of 9.81. So this is 12.53 times the square root of h, or h to the 1/2. And this is h. Hey, here's a test. Yours, in fact. What if I just gave you a random test? Okay, so we have the speed, the mass flow rate. So this is the mass flow rate in. This is not the mass flow rate out yet, but the mass flow rate out is equal to the area, and that is given somewhere 0.005 times the speed divided by the specific volume coming out, and that's given. And so that's 5 times. So that's 62.65 h to the 1/2. And so now we can say dm dt is equal to mi dot minus me dot. And so that's 40 minus 62.65 h to the 1/2. Okay, so that's part A. And then part B is just plugging a value into that. So dm dt when h is equal to 0.5 is equal to 40 minus 62.65 times the square root of 0.5. So negative 4.3. And that's kilograms per second. Any other questions on this test? If stuff comes up later, we can do them next time or whatever. All right. So now we're going into the last pretty short topic for the second law of thermodynamics. And that is the second law for control volumes. And this looks like d capital S dt for the control volume is equal to the sum of all the Q dots over the temperature at the boundary plus mi dot times the specific entropy at the inlet minus me dot times the specific entropy at the exit plus the rate of entropy production. And this has to be greater than or equal to 0. It's equal to 0 if there's no irreversibilities. And since this has to be an isolated system, that means reversible, not just internally reversible. And okay, so we can use this for the same kind of stuff we've used the second law for before. We can, if we get a big number for this, we know that there's a lot of inefficiency that we can try to fix. And we can also use this to figure out the direction that a process can possibly move, because we know this can't ever be negative. Okay. Like always, we're often going to use this in steady state. So what does steady state mean? Yep, perfect. So it means that any property has no rate of change, so this is equal to 0. Also, steady state, because of the mass balance, says that mi dot is equal to me dot is equal to just the mass flow rate. So we always see that in these control volume things. And then third, it means that there's some interchangeability in the way things are described. So sigma dot over m dot is equal to sigma over m for any time interval. And similarly, q dot over m dot is equal to q over m for any time interval. Okay, so the ones in 3 are often just going to come about in the way data is presented to you, or the way the answer is asked for. The way the answer is question is asked. All right, so for first example, let's say we have a turbine in steady state. And steam enters and a saturated vapor exits. At state 1, well, at the inlet, we have that the pressure is 30 bar. The inlet temperature is 400 degrees Celsius. The volume, no, not the volume, the speed is 160 meters per second. And then at the exit, remember this is a saturated vapor, so we don't need as much information to look stuff up. We have P exit is 1.01 times 10 to the 5th, 1.01 bar. The temperature at the exit is 100 degrees Celsius, and the speed at the exit is 100 meters per second. And if we're given that over some time interval, the heat transfer per mass is negative 22.6 times 10 to the 3rd joules per kilogram, and the outer surface temperature is 350 Kelvin. What's the rate of entropy production over the mass flow rate? So this is a question where we're trying to figure out the efficiency of this system. After you do this, you get this number. You try to figure out what this number would be if you changed certain things. What if we reduce the inefficiency here, 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 compare that number, and you're just trying to get that number low. Okay, so the second law for control volume says ds dt is equal to the sum of all the Q dots over temperatures around the boundary plus, this is in steady state, so I'll just call this m dot times the quantity Si minus Se plus sigma dot. And since it's steady state, this is equal to 0. So we get 0 is equal to, what can we say about the heat transfer? I'm going to divide everything, since we're doing everything as ratios of properties divided by masses, and we're given this heat transfer divided by mass, but we can think of that as Q dot over M dot. I'm going to rewrite this as 0 is equal to Q dot over M dot divided by the temperature plus SI minus SE plus sigma dot over M dot. And a lot of these problems are going to be, you're going to be calculating stuff as a ratio, divided by the mass flow rate. So you're going to take this step. Okay, the heat transfer occurs at the outer surface. Our system is the device. And so our Q dot over M dot is negative 22.6 times 10 to the third divided by the temperature, and the temperature at the boundary is 350. Now we're close. We just have to use a table to look up. This is steam, so it's water. So we have tables for all this stuff. So now in the tables, we just have to look up these specific entropies. At the inlet, we have a temperature and a pressure, so we can look it up. At the exit, it's a saturated vapor, so we actually have more information than we need. So from a table, we have that the specific entropy at the inlet is 6.92 times 10 to the third joules per kilogram Kelvin. And at the exit, 7.35 times 10 to the third joules per kilogram Kelvin. And so 0 is equal to, that first term comes out to be negative 64.57. Everything's in SI units. Plus 6.92 times 10 to the third minus 7.35 times 10 to the third plus sigma dot over M dot. And now just solve for sigma dot over M dot. And you get 498 joules per kilogram Kelvin. And if you ever get a negative number for this, that should, set off a red flag. That has to be positive, or if you have a reversible system, 0.
Most of the time, would we just remove the negative, like we messed up a sign?
No, I would not do that.
Okay.
I think probably that tells you that, sometimes that can be the case, but it means that somewhere you made a mistake.
Not
and
like other things we've done.
Right,
Yeah.
right. Okay, so that's trying to find how much inefficiency you have. The other thing you can do is use this to determine the direction that a process happens. So let me do one like that. So let's say we have a device that exchanges enthalpy change for fluid speed change. So what are the two possible devices that this would be?
A pump and a
Nope.
no. Is it a nozzle?
A nozzle or
Diffuser.
diffuser. Yep. Okay, so let's say that it's steady state. We're going to make this simple. There's no heat transfer. There's no work. No significant change in potential energy or significant change in kinetic energy. So we have this really simplified form. And we're given that at one end, we have steam at a pressure of 60 bar, a temperature of 400 degrees Celsius, a speed of 30 meters per second, and at the other end, we have a saturated vapor and a pressure of 30 bar. So we don't know whether it's going from that 60 bar state to the 30 bar state or vice versa. And the question is, which way is this going? Is this a nozzle or a diffuser?
Silly question, but when would you not know that? Like, when would you use this?
Yeah. Let me think about that for a second.
Sorry.
No, I mean, I know that's occurred to me before too, and I've thought about it, but not for a while. Let's see. Well, practically speaking, for me, this is something I can do when I'm making up problems to make sure that I'm giving possible states, to make my problems more realistic, because if you're just thinking of things in terms of the first law, this could happen either way, no problem, So that's something that
I'm just thinking like practically.
use it for practically, right?
Well, so if you were like designing some sort of like refinery system,
Uh-huh.
it's like you knew you had like this boiling hot
Uh-huh.
of
Yeah.
kerosene on one end.
Right.
You wanted to make sure that the things that you were going to do were actually
right.
like it was going to come out the other side.
Yeah. I suppose if you have like design criteria you're trying to meet, you could check to see whether what you're trying to do is even possible this way.
Okay.
I have this is pretty out there, but I think it's kind of interesting. Like there was sort of a Stephen Hawking book just written for like a general audience that was talking about how like there really might not be any such thing as time at all, like that really everything is just happening is all happening together, and that the only reason that we experience the feeling of time is because the processes that go on in our brain entropy increases in our brain and so we experience time to be the increase of entropy, like
Interesting.
so, and that was like used as a explanation for, yeah, like if like there's all this physics that just says like, yeah, that this time thing doesn't really make sense in some ways. Like, why do we experience time? It could just, okay, so I don't remember the book very well, but
There's your answer.
Does that like check out though? Like on planets that experience time differently, is entropy happening differently?
and as far as we know, entropy definitely always goes up everywhere. Yes.
Got it.
Um,
Just the rate.
but yeah, so if there's no, yeah. Okay, so
I don't want to do the calculation.
Back to like, how is this practical? It's practical in determining whether it's possible to build a thing that goes from certain properties to certain other properties.
More to check than
Yes. I think I really don't know what cases are where you'd be where like a company would be like, we found this thing like it does. I don't know. It's hard to imagine anything like that, but I mean, it's interesting that this is the first way that you've ever seen since you first saw conservation of energy to determine the direction of a process. Like, that's just an interesting fact, you know. But yes, I've wondered that same thing, and I was just trying to remember what I concluded from it, and I think my only conclusion was like, oh, well, it's useful for me writing problems because I can make sure that the problems I make are possible, you know.
Okay.
Well, I'm guessing that's what it is really.
Mhm.
It's like you're not saying like, oh, what is this device?
It's
Mhm.
a proof of.
Yeah, but it's like, okay, like I
Mhm.
want to do this thing and I
Yeah.
have these,
Yeah.
these objects.
Mm-hmm.
It's like before I build it,
Right.
I should
And
probably check that.
beat
it's
my
even
head against the
possible.
wall because I can't meet these criteria. Yeah. That seems like I can't come up with a better answer than that. That's
just
for
like
sure.
That's like
Yeah.
a test way to like make sure
Right.
that you can do that.
Yeah. Okay. So now we're going to do this problem anyways because,
No more questions.
okay. Yeah, no more questions.
Ever.
Okay, so let's try nozzle. So that means that our state 1, our inlet, has its superheated steam. The pressure at the inlet is 60 bar. The temperature at the inlet is 400 degrees Celsius. The speed at the inlet is 30 meters per second.
You just got that 60 bar for the table.
No, it was given.
Was it?
Yeah.
Are you sure?
I don't have that.
I have it written right here.
Oh, gotcha.
Calling me a liar?
Yes.
I guess so. Exit is a saturated vapor, and P exit is 30 bar. And so, like with the last example, we have everything we need to look stuff up. The first law says d E dt for the control volume is equal to Q dot minus W dot plus, this is steady state, so M dot times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. And we're canceling some stuff. Said there's no heat transfer, no work done, no changes in kinetic or potential energy, and it's steady state. So we have that, well, did it say, oh, you can't do a calculation with nozzles and diffusers and ignore speed. So, sorry, I made a mistake here. So cross that out. There's no, cross out the thing about kinetic energy. We're going to include that. I know.
We're even now.
Yeah. And so now divide out the mass flow rate, and you get that HI plus VI squared over 2 is equal to HE plus VE squared over 2. And we can look up these H's. So use a table for H inlet and H exit. And we get 3177.2 times 10 to the third plus the inlet speed squared, assuming that this is a nozzle, is equal to 2804.2 times 10 to the third plus VE squared over 2. And we're using this to calculate the exit speed. And you get 864.2 meters per second. Okay, so that's what this device is doing. And remember, this is pretty similar to like the flow of these problems. I didn't even ask for this, I don't think, but
I've got a super quick question.
yeah.
So then if we decided to do it the other way, would that just become the inlet?
Yeah, nothing would change so far because all we've used is the first law. But like the flow of these problems often is you're going to be asked to use the first law for control volumes and then the second law for control volumes to find something out about directionality or efficiency. Okay, and so I didn't ask for this, but you got it anyways. So now we're going to do the second law. And the second law says d capital S dt for the control volume is equal to the sum of all the Q dots over temperatures around the boundary plus M dot times specific entropy at the inlet minus M dot times specific entropy at the exit plus sigma dot. And all we're doing is looking to see whether this comes out positive or negative. If it comes out positive, then we guessed right, this is a nozzle. If it comes out negative, you can assume that it's a diffuser, or you could, if you want to be extra careful, you could go back and recheck. But, well, all it's going to do is change the signs of things, so there's no need to recheck, I guess. If that comes out negative, you just know that you have your inlets and your exits switched. Okay, and steady state says that's 0. We were told there's no heat transfer, so this is 0. So I'm going to, again, divide everything by m dot. So we have 0 is equal to SI minus SE plus sigma dot over m dot. We've already used the table. So, oh no, we didn't, not for specific entropy. So now the table for the specific entropy values say, well, let me, so we can say S at the exit minus S at the inlet is equal to sigma dot over m dot. And the table values are 6.838 times 10 to the third minus 6.187 times 10 to the third, and that's greater than 0. So since m dot is always greater than 0, that tells you sigma dot is greater than 0. And so it's a nozzle. So on these things, you know, expect to use the first law for control volumes and then the second law of control volumes to tell you something about. So first, you'll use the first law to calculate some value, then you'll use the second law to calculate either the directionality or just the, you know, some rate of entropy production. Anybody have any questions about that? Okay, that's the end of the second law of Thermo.
Hooray.
Yeah. Now we're going to get into some more practical stuff. Before I get into the next topic, I'm going to spend the next couple classes just going through a careful outline again. I've done that a couple times, but I think it's helpful to just keep going back to these outlines. So let's stop for today, and then we'll just get into, and the way I'm doing these outlines, I never really decided to do it, but I seem to be kind of one by one, like formatting stuff in a different way. Maybe that's worse, but it's sort of like different ways to think about how to categorize these things. Just kind of, I don't know, feels like brain exercise that's probably helpful. Okay, that's all.